As computer scientists, one of the biggest questions we face, whether we're a researcher in academia, an engineer in industry, or a student in university, is, does my program work as expected? Typically, we rely on tools like testing and observation to evaluate code robustness. But no matter how many edge cases we consider or how long we observe a program, we can never answer our question with 100% certainty. Yet, what if we told you that there are methods we can employ to truly understand exactly what our program does? Hi, we are Adrian Lindell, Erica Liu, and Jeffrey Moon, and we're a part of UCSB's Verification Lab. For the 2022 through 2023 academic school year, we focus on the field of software verification and its applications to devise our research, advancing binary analysis through compositional symbolic execution. Now let's dive a little deeper into what we mean.
Symbolic execution is a static analysis method used to analyze program behavior. Instead of executing the program with concrete values, we can substitute symbolic variables as placeholders for these values. This is similar to algebra, where the variable x can be used as a placeholder for any number. Symbolic execution steps through the program and traces the logic applied to these symbolic variables. When it reaches a branching point, such as an if-else statement, it will add the branching condition to a Boolean expression that represents the current program path. This process continues until the path terminates, and the resulting Boolean expressions will represent all possible program paths. These expressions represent a program's behavior, which is useful for software testing in comparison to other programs. However, each time we reach an if-else statement, there are two new paths. This exponential growth leads to the problem of path explosion, one of the main limitations of symbolic execution. Current modern software systems are extremely complex, ranging from millions of lines of code to distributed systems. Thus, though symbolic execution has strong applications in program analysis, its scalability and efficiency problems prevent it from being more widespread. To address symbolic execution's resource limitations, many efforts have been created to address them. One in particular is compositional symbolic execution.
Compositional symbolic execution, also referred to as CSE, is an expansion of regular symbolic execution in which a program is divided into individual components or functions. Rather than analyzing an entire program in a monolithic manner, it symbolically executes each component independently and then compiles the results. This approach allows for the reuse of previously computed components, reducing redundant calculations for expensive sections of a program at the global program level, and addressing the overhead scalability issues for symbolic execution. Compositional symbolic execution has been implemented for programs with access to source code, yet cases arise where access to source code is limited or inaccessible. In these situations, binary analysis can be used to analyze the programs, and this has applications in research and cybersecurity for malware. Yet, an implementation for compositional symbolic execution for binary programs has not yet been achieved. Why? Well, binary programs lack the high-level semantics that source code programs have. For example, recognizable variable names, defined program structures, and etc. Secondly, compiler optimizations add variability to the control flow of programs. And lastly, binary code has a lot of dynamic behavior, pointers, addressing, registers, and this makes extracting symbolic information even more challenging. Certain binary analysis platforms, for example, BAP or Anger, allow for easier binary analysis by providing a suite of tools to navigate through a binary program. Yet, even then, none have implemented compositional symbolic execution.
Thus, we arrived at two main research questions. One, can CSE be integrated into a binary analysis platform, in this case, Anger? And two, will CSE improve the efficiency and scalability of binary symbolic execution and analysis? As the use of CSE with binary code has not yet been explored, our implementation explores the potential of CSE in analyzing binary files. We chose to integrate CSE on Anger, a popular open-source binary analysis platform written in Python. Compared to other binary analysis platforms like BAP, Anger has the advantage of higher memory efficiency and more built-in analysis tools, but the incomplete documentation added challenges to our implementation process. we had faced some other challenges specific to working with binary executables. For example, collecting control flows in binaries is much more difficult compared to that in source files. Since there are no function declarations in binaries, we had to find another way to identify the start and the end of each function. In our implementation, we first lifted the binary file into an intermediate representation, something similar to assembly or pseudocode, usually used internally by the compiler to understand source files. This allowed us to identify functions and their return values by generating a control flow graph. Rather than running symbolic execution all the way through the entire program, as we usually do and shown on the left, we performed symbolic execution in the scope of individual functions, collecting path constraints along the way, as shown in the diagram on the right. We then store those path constraints and return values in pairs in the form of bit vectors or Boolean expressions as shown in the bottom right corner of this slide, and save the result summaries in a hash. Later in the program, whenever we see a call to a recorded function, we can then grab the summary for that function from the hash and add that in conjunction with the summary of the entire program, saving the time and resources of running SE again on the same function. In this code example, CSE will provide the same final program summary as traditional symbolic execution by taking some intermediate steps. While traditional SE solves for function add twice, our CSE implementation generates a preliminary summary when it first encounters add, and reuses this summary when add is called the second time, skipping the redundant calculation process. CSE then uses the summary for add as a building block when summarizing min. The same process is repeated with min and its caller, the main program. Although CSE has more overhead costs for generating the preliminary summaries for add and min, it saves more time as the numbers of calls to the same function grows and the summaries get reused for multiple times.
To investigate the performance of the CSE implementation, we tested our program against 5 benchmarks, calculators 1, 2, and 3, and tic-tac-toe games 1 and 2. It was difficult to determine common benchmarks among related works, as many were not identified by name or not open source. Based on previous work related to CSE, we expected our program to have the best performance when used with programs with repeated calls to the same function. We selected benchmark programs written in C or C++, which were likely to have repeated function calls. To further test our program's performance, we used multiple versions of programs similar in implementation but varying in complexity. We assessed our program's performance by correctness as compared to symbolic execution time, and number of calls to the constraint solver. Some benchmark programs we rejected used strings and character arrays, which produced results that were not expected. Mapping symbolic variables to array pointers is difficult, not only for CSE, but other binary analysis methods due to the complexity of memory mapping. Future work in the field of SE and CSE should investigate efficient ways to handle dynamic memory. Overall, the results are promising. The majority of benchmarks had improved performance over symbolic execution, most notably tic-tac-toe 2. Tic-tac-toe 2 has a low overhead and simpler logical constraints, which factored into the improved performance. On the other hand, calculator 1 decreased in performance from symbolic execution. This is due to having fewer calls to the same function and low function complexity, meaning the use of CSE in this situation introduces overhead, which decreases the performance. As expected from previous work, CSE produced the best results when used with repeated calls to the same functions. Future work should investigate the possibility of combining the benefits of CSE and SE methods to handle all types of programs. Future work should also consider performance metrics beyond execution time and number of calls to the constraint solver to gain a more comprehensive understanding of the limitations of CSE and binary analysis.
To close out our presentation, we would like to thank Professor Tevfik Bolton, Laboni Sarkar, and the rest of the verification lab for their guidance. We would also like to thank Professor Deepa Mirza and Chinmay Sonar for the organization of UCSB's ERSP program. Thank you.